This video series goes through the daily problems in this maths calendar that is published by the American Mathematical Society. You can either purchase it through their website or via Amazon. There is a minor error in the problem today in the calendar. The corrected version is this version here. It's essentially asking us to compute an infinite summation, and the abbreviated way of writing that is as follows up here. By definition, when we have an infinite summation here, n goes from 1 to infinity, what that means is this version down here. A sum from 1 to infinity means compute the finite sums from 1 to big N, and then keep increasing big N as large as you can and take the limiting behavior. Put simply, we want to evaluate this expression here, where ... simply means that the pattern repeats. The pattern, in terms of just looking at the green thing here, is the denominator is first 1 times 3, then 3 times 5, then 5 times 7, then 7 times 9, then 9 times 11, and so forth. How do we get this from this? Well, we see that when n is equal to 1, 2n minus 1 is equal to 2 times 1 minus 1, which is 1. And 2n plus 1 when n equals to 1 is equal to 2 plus 1 or 3. And indeed I've listed the first 3 here. When n is 1 we have 1 and 3 on the denominator. When n is 2 we have 3 and 5 on the denominator. When n is 3 we have 5 and 7 on the denominator, and so forth. If we don't have any tricks up our sleeve, then the first thing we do with a new problem is just try it out and see what we can get via trial and error. So we want to compute the limit as big N goes to infinity. We start with just evaluating it for small values of n, just to see if we can find any sort of a pattern that might help us. Here I have evaluated it by hand. The first term is 1/3. The second term is going to be the first term plus what we get when n is equal to 2 here, and that gives us 2/5. The third term is going to be the second term, 2/5, plus what we get when little n is equal to 3, which will be 1 on 35, and that simplifies to 3 on 7, and so forth. We see that the first few terms are 1/3, 2/5, 3/7, and 4/9, and maybe you can already start to see a pattern emerge. Whether by hand or via a computer program, we can evaluate this finite sum for the first 8 terms, and we get the fractions on the right hand side here. When big N equals to 8, this finite sum is 8 on 17, for example. If we look at the numerator, we see that when n is 1, the numerator is 1, when n is 4, the numerator is 4, when n is 8, the numerator is 8, etc. It very much looks like that the numerator is going to be big N. The denominator goes 3, 5, 7, 9, 11, 13, 15, 17, which is 2n plus 1. So at least for the first 8 terms, this finite sum is equal to this expression here. This does not mean the pattern will continue. There are some famous examples of patterns that work for the first 1,000 terms or the first 1,000,000 terms and then break, but it's a starting point. Indeed, we can use this to actually prove that this sum is equal to this via a process known as induction, and that will be the first of 2 methods we give for evaluating today's problem. To summarize, one strategy for solving a summation problem is to evaluate the first few terms, look for a pattern. If you believe you've found a pattern, then you conjecture that that is what the finite sum is equal to, and then, as we do next, we prove by a process known as induction that our guess is correct. If this step fails, then we go back and look for a different pattern. In a sense, we have already proved that this finite sum is equal to this for the first 8 terms, because we evaluated this by hand and showed that this equation holds true for big N equals 1, 2, 3, 4, 5, 6, 7, and 8. We cannot do this forever. We're going to get tired and hungry and eventually stop, and so that process only works for finite n up to our limit of patience. However, if we can come up with an automated way of showing that if this is true for one value of n, then it's also true for the next value of n, then we can let that automated process go and prove it for any value of n. And indeed, that's all an inductive proof really is. So we start our inductive proof by proving one case, the simplest case. When big N equals to 1, our starting point, we have to show that this is equal to this. And we do this simply by evaluating the left-hand side and evaluating the right-hand side and showing that they're equal. And we've already done this before, but it's written out here once again. So we know that this expression is true when big N is equal to 1. And then intuitively, we want to use this fact to prove that it's true when big N is equal to 2. Then when we know it's true for n equals to 2, we want to use that and prove it's true for n equals to 3, and so forth. But we need to be able to do it for an arbitrary n. We need to automate it, so that then we can let the process run on its own, so to speak, and we've proved it for any n. So an inductive proof means we assume that the result is true for all values of n up until a certain value, and then we prove that it's true for the next value. So in this inductive step, big N can be anything we like. Big N might be 1,000,000, it might be 253,978, it can be anything. We don't know what it is, but it's fixed. Assuming that, for example, big N is 1,000, we can assume that the result is true for this sum up until big N equals to 999, and then we want to use that fact to show that it's also true for n is equal to 1,000. And by being able to do this without reference to the particular number, but for an arbitrary number big N, then intuitively what happens is that someone else can come along and first choose big N equals to 2 and apply this, because we know it's true for n equals to 1, and then they've shown that it's true for big N equals to 2, and then they apply this again, and they've shown it's true for n equals to 3, and they apply this again, and it's true for n equals to 4, and so you can see that we therefore have shown that it's true for all n. So we want to prove that this is equal to this, and the simplification with the inductive step is to say that, well, we have to show that this is true, but we're allowed to assume that this expression is true when big N is 1 smaller than its current value. And so in this expression here, I just replace big N with big N minus 1 everywhere. So that gets replaced by big N minus 1, this big N gets replaced by big N minus 1, and this N down here gets replaced by big N minus 1. So we're allowed to assume that this summation is true for the case of big N minus 1. Remember that implicitly big N is going to be a fixed number, like 1,000. And so then when we do this, we can assume that this expression is true when big N is equal to 999. So down here, I know I'm allowed to assume that this is true. And simplifying the right-hand side here gives me this expression here. So given this, can we show that this is true? Start off with the left-hand side. We want to work out what this sum is equal to. Just as we did when evaluating this by hand, we can write this sum as the sum of the first big N minus 1 terms plus the very last term when little n is equal to big N. And when little n is equal to big N, I just replace in the denominator here little n with big N. So this is equal to the sum of the first n minus 1 terms plus the very last term here. Here is when our inductive step can be used. We know that the sum of the first n minus 1 terms is equal to this. That's our inductive step coming in. And so this can be replaced with this. And our sum up to n terms is equal to our sum up to n minus 1 terms plus the very last term here. All we need to do is simplify this expression here, and hopefully it will equal this here. And we do this on the next page. So the sum of the first big N terms is equal to the sum of the first big N minus 1 terms, which by induction we know is this, plus the last term. We now get a common denominator. We see that to make this denominator the same as this denominator, we just have to multiply top and bottom here by 2 big N plus 1. So I've got n minus 1 times 2 big N plus 1 divided by this. And then we expand out the brackets and we simplify, and we get that indeed this is equal to this. And therefore, by induction, we know that this sum is always equal to this for any value of n. If there's any confusion, then go back a few slides and have a look at how we motivated an inductive proof. We're not yet finished because we don't want to compute this finite sum, we want to compute its limit as n becomes arbitrarily large. Because we now know what this finite sum is equal to, we now can replace this limit by the limit of what this finite sum equals to, namely n on 2n plus 1. Intuitively, a limit is determined as follows. For each value of big N, we plot the value of this expression here, and hopefully, as we plot it, we see that this value gets closer and closer and closer to some number, and by definition, that number is the limit. Computing a limit normally requires first guessing what the limit is, and then proving it really is the limit. In this case here, n on 2n plus 1, if I divide top and bottom by n, I get 1 on 2 plus, in brackets, 1 on n. Now intuitively, as n gets larger and larger, 1 on big N gets smaller and smaller. It gets closer and closer to 0. So I'm going to guess that the limit of this expression here, as big N is very, very large, is going to be 1/2. And indeed, you can try substituting values of n in yourself on your calculator. Pick n to be 100, 1,000, 1,000,000, evaluate this, and see whether or not you're going to get a number very close to 0.5. When you first learn limits, you need to learn how to prove limits as follows. There are tricks though that make it much faster to compute limits. So we're guessing that this limit is equal to 1/2. Now to prove it, and in some sense this defines rigorously what a limit is. Intuitively, a limit is what something converges to. Rigorously, it's based on the definition in red. If the limit of this expression is 1/2, then by definition, that means that you give me any error you like. So epsilon, you think of a very small number, like 0.00001, or smaller still. You choose any error you like, arbitrarily small, and I have to be able to find a number, let's call it capital M, maybe 1,000,000, 1,000,000,000, some very large number M, such that for any n, for every single big N larger than this number M, we have to have that this expression here is within epsilon of 1/2. In some sense, it's like having to divide a cake between you and your friend. For some reason, you can't divide it exactly into a 1/2. Instead, what you can do is you can divide it up, so one person gets n on 2n plus 1, and the other person gets the rest, and you can choose the value of n here. No matter how greedy or caring each of the friends are, there's going to come a time when they're not going to notice the difference between one person getting 0.500000001 of the cake and the other person getting 0.499999999 of the cake. There comes a time when n will be sufficiently large that both are happy that they're getting essentially 1/2 of the cake each. Mathematically, this is the value of the expression for a finite n. We claim that it approaches 1/2. That means when big N is very large, this minus this should be very small. Now, whether it's a small positive number or a small negative number, we don't care. So we've got an absolute value here. This measures the distance between this and this. This might be a bit larger than a half, in which case this will be positive. This might be a bit smaller than a half, in which case this is negative. We just care about the distance, hence the absolute value. So, given any epsilon, we have to have a rule based on epsilon to construct a number big M, such that whenever n is larger than this number here, then the expression we care about is very close to a half. It is within distance epsilon of a half whenever n is sufficiently large. Once again, the general process is that first we have to guess a formula for big M. And so we're going to do some calculations here that are not technically part of the proof. They're done on the side of the page to come up with a guess as to what M is. And then the actual proof is going to use our guess as to the value of M and show that it really is true. Tangentially, this is why sometimes it's difficult to follow someone else's proof. Yes, you can check that their proof is correct, but you might not know how to construct the proof yourself, because often in doing a proof, you actually have to do some temporary calculations on the side, and if space is a premium, you're not going to show those calculations in the final proof, because they don't affect the validity of the result, they just affect how you came up with the proof. So we want to find a value for big N when this expression is as close as we like to a half. So have a look at this expression here. We simplify it. We say that it's equal to this quantity here. The hope is that as big N is large, this number is very close to 0. And so we first of all check intuitively that that is the case. And indeed we see that the numerator is fixed and the denominator grows as n grows. And so therefore, by choosing big N arbitrarily large, we can make this expression as close to 0 as we like, and hence we believe we're on the right track here, that we can indeed show that this limit is equal to a half. We need to be quantitative though. We believe qualitatively that we can make this arbitrarily small, but to quantify it, we now write down precisely what we need. We need this quantity here to be less than epsilon. We can multiply both sides by 2 to get this. We can then take the reciprocal of both sides, and when we do, we flip the sign here. And when we're dealing with such inequalities, a trick is to not be so precise. We can simplify things by making approximations, because we just require the left-hand side to be bigger than the right-hand side. And so this plus 1 here is just a complication. If 2n is bigger than this number here, then 2n plus 1 will also be bigger than this number here. So for this to be true, it suffices for this to be true, which, after dividing both sides by 2, we see that we just require our n to be larger than 1/4 epsilon, and then we believe that we will have n on 2n plus 1 will be within epsilon of a half, as we require. So this motivates us to choose m to be 1/4 epsilon. This is not part of the proof. The proof starts with this particular choice of m, but this is how we came up with the value of m to try. And there's not one value of m that's correct. There are many different values of m, and in part that's reflected by the approximations we chose to make in simplifying things. So in order to prove that n on 2n plus 1 approaches a half, we have to show that whatever tolerance you have for an error, however small epsilon might be, we can always make n on 2n plus 1 to be within epsilon of a half, provided big N is sufficiently large. But we now have to quantify how large n plus b, how large n must be, and we already calculated on the previous page that we believe as soon as n is larger than 1/4 epsilon, this is going to be true. But we need to actually rigorously prove this. not surprisingly, the steps are going to be very similar to before. If n is greater than 1 on 4 epsilon, then that means 1 on n is less than 4 epsilon, which means 1 on 4n is less than epsilon, and we can use this in here. So how far away is n on 2n plus 1 from a half? Well, if we compute n on 2n plus 1 minus a half, we found that that was equal to negative 1 on 2 times 2n plus 1 in brackets. And when we take the absolute value, the negative sign goes away because the denominator is positive. And expanding the brackets, that's 1 on 4n plus 2. And that is less than 1 on 4n, because when we increase the denominator, we make the fraction smaller. And our calculation shows that whenever n is greater than 1 on 4 epsilon, then 1 on 4n is less than epsilon. And so we have now proved that the limit as n goes to infinity of n on 2n plus 1 is equal to a half. Indeed, this calculation here shows that we can make n on 2n plus 1 as close as we like to a half simply by choosing n to be sufficiently large, precisely greater than 1 on 4 epsilon. Once you've computed limits once or twice from first principles, you find it's very tedious. And that makes us appreciate the theorems we have in calculus textbooks that tell us such things as, if the limit of one sequence is alpha and the limit of another sequence is beta, then the limit of the element-wise sum of the two sequences is just the sum of the limits, alpha plus beta. This is the true too for multiplication and division, etc. And so, to compute the limit of n on 2n plus 1, we can actually proceed as we did at the start, rewrite this by dividing numerator and denominator by n as 1 on 2 plus 1 on n. And then the rules here essentially say that the limit of this whole expression is the same as the limit of 1 on 2 plus the limit of 1 on n. So the limit has gone from the outside, we've brought it all the way in to the inside. You can, in some sense, think of this as a special case of these results up here, in that the 1 up here could just be the sequence 1, 1, 1, 1, 1, 1, 1. The 2 could be the sequence 2, 2, 2, 2, 2, 2, 2. The first sequence has a limit of 1, the second sequence has a limit of 2, and this expression here, for example, is saying that the limit on the outside can be brought into the limit to the inside here, which is all we're doing down here as well. This means that computing the limit of n on 2n plus 1 reduces to just computing the limit of 1 on n. And the limit of 1 on n is very easy to show is just 0. So once you've computed the limit of a few basic things, you can compute the limit of much more complicated things via this approach of bringing the limit from the outside to the inside. Now the calendar actually asks not for this sum, but for the reciprocal of this sum. And because we've shown that the infinite summation here, which by definition is the limit as big N goes to infinity of the finite sums of the first big N terms, we've shown that the sum inside here, its answer is 1/2, and the reciprocal of 1/2 is just 2. There is an alternative solution to this problem. It would eliminate the need for doing a trial and error solution, which we did earlier, and it follows a basic principle in mathematics that when you have an expression, you try to reduce it first to a simpler form. And in this case, we use what's known as a partial fraction decomposition. We want to reduce this expression here into the sum of two simpler expressions. The denominators are simpler in this case and in this case. Can we find numbers to go here and here such that this is equal to this plus this? The theory of partial fraction decompositions basically says that yes, we can do this. If it's possible to write the left-hand side in the form of something on 2n minus 1 plus something else on 2n plus 1, then we can take the right-hand side, perform this addition by making a common denominator, and then comparing the left-hand side and the right-hand side. So in order to do this summation here, we want both denominators to be 2n minus 1 times 2n plus 1. So that means I have to multiply the term on the left by 2n plus 1, and I have to multiply the term on the right by 2n minus 1. So I have on the numerator alpha times 2n plus 1 plus beta times 2n minus 1. My denominator will then be 2n minus 1 times 2n plus 1, which is the same as the denominator here. So if this is equal to this, because they've now got the same denominators, I require the numerators to be the same, and we just said the numerator on the right-hand side is alpha times 2n plus 1 plus beta times 2n minus 1, and the numerator on the left-hand side is just 1. So if this is true, then we must have this to be true. Expand the brackets, and we collect n here and a constant term here. While there are many different solutions here, for example, you find any solution you like, I can always add, effectively I can add any number I like to this term and subtract that same number from this term here, and I'll still get this being true. But to do that, that would mean alpha and beta start to involve terms with n here, and we want the simplest possible solution. So can we solve this where alpha and beta do not depend on n? If that's the case, then I require alpha plus beta to be 0, so there's no influence from n here. So I want alpha plus beta to be 0 to get the simplest solution. And that means for this to be true, because this is 0, alpha minus beta must be equal to 1. And this leads me to alpha being a half and beta being negative a half. And while this might look a little bit magical, as I said, partial fraction decompositions mean that, generally speaking, you can always do this. It's not clear how much this will help, but for this particular case, it actually allows us to solve the problem very easily. This expression here, our original expression, is the same as a half times 1 on 2n minus 1 minus 1 on 2n plus 1. Here I've got my numerator as a half, and here I've got my numerator as minus a half, which is what we found by doing a partial fraction decomposition. Now, to actually evaluate it rigorously is a little bit messy, but if we just expand this out by hand, we see there's a very basic and simple pattern that leads almost immediately to the answer. Look at this term by term. When little n is equal to 1, this will be 1 on 1 minus 1 on 3. 1 on 1 minus 1 on 3. When n is equal to 2, I'm going to get 1 on 3 minus 1 on 5, this term here. When n is 3, I'm going to get 1 on 5 minus 1 on 7, and so forth. And the key point is that when one term has a minus 1/3 here, the next term has a plus 1/3 here, and they cancel out. And when the next term's got a 1/5 here, it's cancelled out by the following 1/5 here. And so we can write down almost immediately that this is equal to, well, a half out the front, of 1 minus 1 on 2n plus 1, because all the other terms cancel out. To do this formally, then you take this summation here. By seeing what we did this way, that tells us the algebraic manipulations we need to do. For the first sum, we need to take out the very first term, but keep the rest. So this summation here, I've taken out the very first term, which is 1, and then I've kept the rest from n equals 2 to n. For the second sum, I want to keep all the terms as a single sum except for the very last one. So therefore this term here I break up as a sum from n equals 1 to big N minus 1, and then I isolate the very last summation here. And the reason I do this is because as we've seen that these sums cancel. So I've got this is equal to this, and we believe that this and this should cancel. They should just disappear. The way to do that formally is I take this summation here, which is currently from little n equals to 2 to big N, and I need to rewrite it by changing little n to go from 1 to big N minus 1. And I do that if I shift n, if n should start off at 2, but I want n to start off at 1, then that just means I have to replace in here, I have n plus 1 instead of n. So when my little n is equal to 1 here, then over here I get my 2, which is what I need over here. So by simply shifting by 1 my summation here and making the appropriate modification so that it's still the same sum, I see that this term and this term are now the same, and so they cancel, and so I'm left with my 1 minus 1 on big 2n plus 1 as we saw from here. Our claim then is that this summation here is equal to this expression here, and it looks a bit different to what we found from before, but indeed it's the same thing. To verify, earlier we got this expression for the sum, now we got this expression here, but a simple algebraic manipulation shows that it's indeed the same thing.